fourth day. So today the goal is to, let me just summarize what we've done until now again. We're trying to understand this picture, right, which is the phase diagram of the Spike-Wigner model. And so there are three curves on this picture, which represent the mean square error reconstruction of some estimators as a function of the signal-to-noise ratio. The black one is the minimum mean square error, which has this discontinuity somewhere there that separates the statistically impossible region where it is 1, as bad as it can be, and then it's not 1 anymore, and the transition between the two is the information-theoretic threshold. And the goal of today will be to obtain a formula for this curve. So we're going to derive the mutual information of the problem, and then by the IMMSE formula, we'll directly get access to this curve here. Okay. Something we've already done is to study the blue curve, which is the performance of spectral PCA, and to do so, we've used random matrix theory, and in particular the theory of the BBP transition, which is this transition that separates the regime where the spectral estimator corresponding to the eigenvector with largest eigenvalue in the data. This BBP transition separates the region where it's 1 anymore. Okay. And there's a third curve, the AMP curve, which is an efficient Bayesian algorithm, which also has a discontinuous transition like the MMSE, but at a higher signal-to-noise ratio that I called lambda algo, which matches in this specific case the BBP transition. And by case, I mean the specific prior for the signal. So the blue curve is analyzed, and the black curve is what we're going to do, and I will discuss a tiny bit the red curve tomorrow. Okay. All right. So that's the goal of today. But before, so yeah, the goal is of today. Analyze the MMSE for the spiked Wigner model using the replica method. So again, the goal will be to first derive a formula for the asymptotic mutual information between signal and data, and to use the IMMSE formula, which gives us that the limit, so the derivative of the mutual information with respect to d lambda is 1/2 the MMSE of the rank 1 matrix given its noisy observation in the spike model. And we'll be able to take the limit and show that this is also equal to the limit of the derivative. Sorry, to the derivative of the limit what this limit is there. And this follows directly by the fact that x star y, if I think of this as a sequence of function indexed by the size, okay, these are limit when n go to infinity. This is a sequence of concave functions. And concave functions, the limit of a concave of a sequence of concave functions is itself a concave function, and so in this case you can exchange limit and derivative. Okay, perfect. So really, all this was discussed already. So really, the goal to obtain the MMSE is to obtain the limiting mutual information. Okay, so this is the replica formula that I've discussed at the beginning. Because once we have it, we directly have the MMSE. Okay, perfect. So before doing this, let's look at a simpler problem. Where we do not need the replica method. Okay. Just to see the difference. And this problem is again the ferromagnetic Ising model that we discussed yesterday. So the Hamiltonian of sigma is minus j over n sum I different than j, and I can divide by 2, summing over I less than j or I different than j, and dividing by 2 is the same. Yes, and perfect. And we had also an external magnetic field. Okay. So the Gibbs measure, you remember, or the Gibbs-Boltzmann distribution is P sigma equal exponential minus beta h sigma divided by the normalization. Okay. And the object of interest here would be to compute the free entropy, which is just the log partition function. Let's take beta equal 1 for simplicity. From now on, it's just we drop one symbol, okay? But you can carry it if you want in the analysis. The free entropy would be 1 over n ln of z, and we want to look at its limit. Okay, so that's the goal. So let me show to you that in this very simple model, and by simple I mean it's one of the simplest statistical mechanics problem, but it's still a complex model, not in the sense of its analysis being complicated, but it's still complex because it's representing large populations of variables interacting in a non-trivial manner through these pairwise interactions. And therefore, there is complexity and there is a phase transition, as we've seen. We have different phases. We have the ferromagnetic and paramagnetic phases, okay? Depending on whether the magnetization, which is the average magnetization, the sum of the spins divided by the number of spins, is zero or non-zero. So it is a complex system with phase transitions, but its analysis remains simple, okay? So I want to show you that in this case, you don't need fancy tools. You can just solve it directly. And we will, in the Spike-Wigner model, in contrast, you cannot do what I'm going to show you. And therefore, you need a smarter method, which is the replica method. Okay, so easy solution. Let's see how it works. Maybe some of you know already this, I don't know. So it's very simple because you see, once you identify, the key point is to identify the order parameter. So by identify the order parameter, it means identify the quantity which is enough to track, to analyze, to keep track of in order to solve the model. And here the model, the Ising model, tells you right away what it is, because you can simplify it very easily if you see it. So let's see. You see that I can rewrite. So the magnetization that I remind you the definition of is the correct order parameter, because you can see it simply from the fact that if you try to simplify the Hamiltonian, you can do so in terms of this order parameter only. What you realize is that the Hamiltonian, the energy function of the problem, which defines the problem, so is just a function of this magnetization, actually. So really, this Hamiltonian is not really a function of the configurations. In this case, it's really a function of the magnetization. Okay, so let's see this, because I can rewrite. So H sigma clearly is minus J. So you see this double sum up to one diagonal term, which I can add and remove, is the square of the sum. So it's the square of the magnetization, right? So this is minus J times N over 2 sum over I of sigma I sum of I of sigma I over N squared. Maybe I can add J over 2N sum of I sigma I squared to compensate for the diagonal term that I counted, but this is just a constant because this is equal to 1. And a shift, like a constant, an additive constant in the energy does not change the model, right? Because if you add a constant here in the energy function of a system like this, it means you're just shifting the exponent defining the probability distribution, but this constant, meaning it does not depend on sigma, will simplify with the same constant appearing in the diagonal. So constants in energy functions can be forgotten. They don't change anything. Okay? So this constant, of course, can be forgotten. It will be simplified with the normalization. Minus N H sum over sigma I over N. Okay, so this is indeed minus Jn over 2 the magnetization, depending on sigma, to the squared, minus NH, the magnetization. So you see, yeah, the energy is just a function of the order parameter directly. So it means that actually in this model, the probability distribution of drawing a certain configuration, a certain sigma, does not depend on the value of sigma. It really depends on this macroscopic observable, this order parameter. And so you can simplify, you can solve now the problem directly. How do you do? By Laplace method. Okay, so let's see how do you do. So solving the method, so solving the model. So you want to solve 1 over n, so you want to compute the log partition function. Of exponential, we took beta equal to 1, so exponential minus h, which is jn over 2 m of sigma squared plus nh m sigma. I can even already factorize the common factor m. Okay, so this is the problem I want to solve. And why can I solve it easily now? Because you see, as I've been able to express the energy in terms of m only, it gives me a natural decomposition of the space of configurations over which I'm summing here in terms of subparts, which are what we called yesterday the macroscopic states, meaning subset of configurations with a given value of an order parameter, in this case the magnetization. So, and then we can exploit this. So let's see. So I can rewrite this as 1 over n log sum over all possible values of the magnetization, okay, which at the moment n is finite, is a discrete set, right? Because the number of spins is finite, so therefore the magnetization can only take a finite number of values, but it's and sum over the associated macro states, meaning subsets of configurations with this given m. So I will write this like this: the set of sigmas such that m of sigma equal m. Okay, and of course, by definition, for each of this sigma, the m sigma is constant. So I can, it means that this exponential inside this sum there is constant. So I can just put this exponential outside there, right? So let me do it. One, right? Perfect. And essentially the problem is solved now. Why? Because this thing you can compute easily. Okay, this is just a problem, a combinatorial problem. You have a sequence of binary variables, plus and minus ones. You're fixing their average, m, and you're counting the number of such configurations with that given average. So it's just an exercise that you solve in the first courses of combinatorics, And of course, so this term in physics is what is called the entropy. Okay, so it's actually the exponential of the entropy. So I can write this as the exponential. Actually, it will be exponential in n as well. So this is exponential n times a certain function that I will call s of m. And if you do the exercise, what you realize is that this s of m is the binary entropy. So it is minus, it is 1 second, I don't remember the binary entropy is, yes, is minus 1m over 2 log of 1 plus m over 2 minus 1 minus m over 2 log of 1 minus m. So this is a very simple exercise. If you've never seen this, you should try it, but it's a trivial thing to show. So this term is counting the degeneracy that we call the entropy in physics, the entropy of this value of order parameter. So it's counting, the entropy is basically the exponent that correspond to the number of configurations, sigma, with a given value of the order parameter m. Okay, and of course this number is exponentially large, because given an m, you have exponentially many such choices of sigmas that correspond to this m, and the exponent is called the entropy. Okay. Perfect. The other term now is the energy, and it's already there. Okay, we don't have anything to compute anymore. And the energy here is also expressed as a function of the order parameter. So now we're in a position to solve. So we have obtained 1 over n log sum over m of exponential n times the energy, which we managed to express directly as a function of m. Oops, excuse me. Yes, and I'm sorry. Yes, this is minus the energy, excuse me. Plus, so I can factorize the n. Plus the Sn. And that's it. Now the problem is solved. Why is the problem solved? Because what I obtain is precisely the type of sums, or this will become an integral when n becomes large, because here it's a sum over all possible discrete values of m that are between 0 and 1. Between -1 and 1. -1 corresponds to all the spins down, 1 is all the spins up, and then you have all the possible values of the magnetization in between. And when the number of spins goes to infinity, this becomes a continuum. So in the limit, this will become an integral. So we have the integral, or the sum of an exponential, of exponential terms, which are proportional to n, which is very large. So how do you evaluate this kind of integrals? I've already given the answer, but this is precisely the form where the Laplace integration can be used. So basically, Laplace is just telling you that when you are summing exponentials, which are very large, and you take the order of the exponent going to infinity like this, basically only the term that dominates matter. there is only one term in this sum or this integral that matters because it is exponentially larger than all the other terms. Okay? So if you sum exponentials which are large, and the exponent of these exponentials are large, and you let it grow arbitrarily, basically only one exponential in the sum will matter because it is exponentially larger than the others. Okay? So this, when n becomes very large, is approximately equal, and it's an equality when n goes really to infinity, a log of exponential of n, the max with respect to m of this exponent. Okay, so here I'm using Laplace integration. Okay, which is a simple version of saddle point integration in the real plane, in the real for reals saddle point integration. These are, of course, saddle point and Laplace are not exactly the same thing, but they both rely. Saddle point is more general. You can extend, you can integrate in the complex plane, but it's also relying on the fact that you have large exponentials. Okay, and that's it. So this is equal when n goes to infinity. So this is equal. So the log and the exponential, they simplify, and this n with the 1 over n, they simplify, and so this is max of Sm minus Hn. J over 2n squared. Plus Hn. And the entropy is written there. I will not rewrite it explicitly. It was minus Hn. And that's it. So you have reduced the computation of this high-dimensional sum, or which is the log partition function, into the problem of solving a one-dimensional optimization problem. Okay? And if you do so, if you solve this problem, let's say the solution, let's say that the m, so this gives the free energy, and of course the argmax of this thing is, let me call it m0. It's really, it's what we call the equilibrium value of the magnetization. So it's the magnetization you would observe at a given choice of J and H in the problem. If you were, let's say you simulate this model for large n at a given value of J and H, and you, by Monte Carlo, you sample a configuration of the Gibbs measure, configuration sigma drawn from the Gibbs measure when n is large, and you compute the empirical magnetization for this sigma, you would realize that this is extremely close to this, to the minimizer of this formula. It's the equilibrium magnetization. Okay? So you see, we could compute in this case easily, we could solve the problem easily, and we have access to everything. Okay? And this m0 as a function of h is what we drew yesterday. So if we fix h, let's even take h equal to 0 as a function of j. We've seen there was the plot we've done was as a function of beta. But okay, in general, this is also a function of beta. If you track beta, and as a function of beta, you remember we had something like this. This would be the M0 as a function of beta at fixed j and h. Okay, so the solution of this simple scalar optimization problem gives you access to this order parameter for this complex system. And really what allowed us to solve the problem directly without using any fancy tool apart from Laplace integration, which is not a fancy tool, is that the original is that the Hamiltonian defining the problem is already written in terms of the magnetization of the order parameter. So of a statistics which is an average over the spins. And so we could solve by Laplace. Okay. But in general, this is not the case. Okay, you cannot identify directly in the Hamiltonian some simple quantity, some simple statistics over which you can integrate like this. This trick only works for a very simple model like this ferromagnetic Ising model. Okay, is it clear what I've done? Okay, so okay.
Any questions from audience?
It seems someone answered that it's clear. I will assume that's the general feeling. Okay, so now let's go back to the spike Wigner model, which is more complicated and for which you cannot do this. Okay. Perfect. So now the spike Wigner model. Where we will need the replica method. Okay. So let's rewrite the problem. I just want to use the same notation as in the course. Yes. So the posterior distribution in the model, if you remember, is P of X given the data matrix Y is proportional, so up to normalization to the prior, which is factorized over the xi elements by assumption. And then we have product over all pairs, so which are related to our observations. Oops, then there is a bug. Exponential minus 1/2 Yij. And we have our Gaussian likelihood coming from the fact that the noise is Gaussian. Okay, so this is the posterior, which I can simplify a bit. So normalization that will depend on my data that I call Z to use the statistical mechanics notation. And here what I can do, again, like for the Ising model, any term in this exponent which does not depend on x is what I call a constant and can be absorbed can be simplified with the same constant in the normalization. Okay, so I can get rid directly of all terms here that do not depend on x. So if I expand this square, for example, y squared will not depend on x. It will depend on the true x, but the true x is not is a constant. We are talking about the probability of this little x here, while here inside there is the x star, really the value of the ground truth signal, but it doesn't matter in this probability distribution, this term that depends on x star and the noise only. Okay, so the y squared term can be simplified with the normalization. Then we have the cross term that depend on x, and then we have the square which depends on x. So we need to keep only these two last terms. So I can rewrite this as the exponential of minus an Hamiltonian, if you want. That will depend on x and y. This is my energy function, because now if you want, I'm casting the problem in the statistical mechanics notation in order to use its techniques. And what is the Hamiltonian? It's minus the log likelihood, okay? Minus log likelihood. You get the Hamiltonian. Okay, so that's the definition of the problem, and I can also expand, remembering that this y was equal to square root lambda over n. Of course, in practice, you cannot write down this decomposition because you don't have access to x star and the noise, but here we are doing theory, so we can decompose y like this. It is how it was constructed in our theoretical model, and we are analyzing what is going on. So I can use this decomposition when doing theory. Okay, so in this case, Hamiltonian becomes this. The star is for the ground truth. And the Z is our Wigner matrix corresponding to the noise. So you see again, we have this planted term, the signal component. We call this the planted term or signal term. And this is the noise or disorder term. Okay, in the SK model, this planted term corresponds to just the ferromagnetic bias, and it does not depend on Ij, it's a constant. Instead, here it depends on Ij, and we have this term also in the SK, in the spin glass. Okay, perfect. Like an average or like a magnetization. This is not the case, right? Because even if we have a double sum here, so here we have something that looks like a magnetization, but not here. So let me just emphasize that point. The first term, so let me forget this for a second. Oh, okay, let's put it. We have a term in the Hamiltonian, let's call it T1. We have a term like sum of I less than j that I can write as I different than j of xi star, xj star, xi, xj. And this is indeed, like in the Ising model, something that looks like 1 over n over 2, 1 over n sum of I, xi star, xi to the squared minus a diagonal term. But we have this magnetization that appears. This is like a magnetization. I can call this the M of x, but you see it's a magnetization in the direction now of x star. Okay? But this looks like a meaningful order parameter, and it is one. It is very important to track, because actually the value, this magnetization tells us how much a posterior sample is aligned with the ground truth. So it will be related to the errors that we want to compute. It's an important quantity. But unfortunately, we have also that term, the disorder term. And you see, because this is a full rank matrix, the sum over ij of this term, I cannot decompose this as a square of a single sum. So due to the non-trivial structure of this matrix, this one is rank 1. And because this matrix is rank as rank equal to 1, I can get this decomposition. But this matrix is not rank 1, so I cannot decompose this sum in a simple manner. I have to deal with it. Okay, so that's why you cannot use the Laplace method. Okay, the term 2, the noise term, cannot be written in terms of simple order parameters like m. Like the m of x I just defined here. So I have to find another approach. I cannot do a direct calculation like in the Ising model. Okay, that's why you need the replica method. So somehow we need to get rid of this noise. We need to integrate it out. Okay, this is where the replica method enters. Okay, so let me explain. So goal, get rid. Sorry, are there questions? Get rid of the noise, and by get rid I mean integrate it out somehow, and hopefully this should make appear an order parameter. Okay, so let's see if that's the case. So the starting point for this is the replica trick. So let's start now really the replica method. The first step is the replica trick. So I will always tell you what is exact, what is mathematically justifiable and what is not. The replica trick is mathematically correct. Just you can write the replica trick in various ways. Let me write at least 2 ways or 3. I will write 3 ways. Let's say that, so now our goal, again, the ultimate goal really is to compute, like for the Ising model, the free entropy, okay? Because you remember the free entropy in the context of inference, the average of the log partition function, where the partition function is the normalization of the posterior, there, is essentially the Shannon entropy in the problem. And if you have the Shannon entropy, you have the mutual information. So compute the Shannon entropy or equivalently the mutual information. They're all related, or equivalently the so-called free entropy in physics language, which is really an expectation with respect to the law of the data of the log of the normalization of the posterior, which is the evidence, which in this case I called z of y. Okay, and you see that this is up to a minus sign, and maybe so this is essentially minus the entropy of the data, because this is almost up to, this is the p of y. So there are some constants missing. You can look at in the notes. I don't want to go in these details, but up to trivial manipulations, this is an equality. Okay. So the free entropy, so the log partition function from physics, like we computed in the Ising model, really is nothing else than the Shannon entropy of the problem. And if you have the Shannon entropy, you have access to the mutual information and therefore the MMSE. So that's the goal. Okay. So why is this a hard task? Okay. First, because as we've seen, we cannot employ a direct Laplace integration. There is no simple trick here that allows to simplify this term in terms of an order parameter. So we need to deal with this z. And the problem is how to do that. Okay, so you see when I said dealing with this z, we want to integrate it out. And this integration is indeed present in the problem. We do need to integrate it out because it's inside this expectation. This expectation, the expectation over the data, can be written equivalently as an expectation over the ground truth. The data is a function of the ground truth and the noise. So this is the same as an expectation over the ground truth and the noise. And here is this expectation that we need to carry out. Okay. So the replica trick, I will just write it down and stop there before continuing later, is the following exact identity, which is not which is true for any random variable z of y. So the expectation with respect to some random variable, in this case y, but this could be anything. You can completely forget the statistical mechanics problem if you wish. What I'm going to write is true in general. Of the log of a certain function of this random variable, where again this function can be anything, can be written. See, the hard part is that we have to compute the expectation of the log of something. And in general, this is hard because the expectation is a linear operator. The log is not, so you cannot switch them. You cannot push the expectation inside there. Computing expectation of nonlinear functions of random variables is in general complicated. Okay, so you have to find a way out. And the replica trick is just the following identity. Which you can also write equivalently. All these identities can be verified by Taylor expansion in K. Which is also equal. So you choose the form that you prefer. They are all equivalent. Okay, so you see, so first we'll ask you to check this. Check by Taylor. It's just Taylor expansions in K. And you see that the point of all these expressions, they're now computable, or I will show you that they are computable, because now you see what appears is not anymore an expectation of the log on the right hand side. It's always the kth moment of this random variable. We have the expectation of this random function z to the k. So z is a random variable, instead of computing, if you want, the log moments, this is like a log moment of this random variable z, now you have the usual moments to compute. Okay, so you have this z to the k here, expectation of z to the k, so it's just the kth moment. Of course, the mathematically difficult part is to make sense of what's the kth moment of a random variable when k tends to 0. Okay, and this is where things become a bit subtle. But think for a moment as k as a finite integer. These are just usual moments of this random variable. Okay, so we kind of got rid of the log in a smart way by introducing this kth moment, but the price we pay is that we'll have to make sense of these moments when k goes to 0. Okay, so this is called the replica trick, and it's the starting point, and we're going now. The goal will therefore be to compute this kth moment and then to make sense of the limit k going to 0. Okay. All right, so that's the idea, and we're going to continue later. So we start again in we start again at 1:30 for you. So in 1 hour.
Yes, sir. Yes, sir. We can start. Yes, sir. Yes, sir. We can start in 1 hour.
Okay, in 1 hour we meet again.
Okay. Sir, may I request everyone to kindly switch on their camera for a screenshot? Okay, thank you. We would like to see more faces.
I think most of the others are ghosts. I'm not sure they exist.
Okay, sir. Thank you. Thank you for giving your time, and then we will be back in 1 hour.
Yes, see you later.
Oh, okay. Thank you. Bye-bye.